You type a URL, hit enter, and a fully rendered page shows up in a few hundred milliseconds. That instant feels like magic, but underneath it's one of the most carefully engineered pieces of software most of us touch every single day. Chrome isn't one program. It's a small distributed system running on your laptop, a dozen or more separate processes, each with a narrow job and almost no ability to touch the others, coordinating over thousands of tiny messages a second. That design wasn't accidental. It came out of a blunt engineering bet Google made in 2008. A browser built on 1990's single-process assumptions couldn't survive a web where every tab runs untrusted code from someone else's server. Over the next few minutes we're taking Chrome apart the way its own engineers describe it, process by process, from the moment you press enter to the pixels landing on your screen. Before 2008, browsers were monolithic. One process ran everything, so one bad plugin or one runaway script could take the entire browser down with it. Chrome's answer was to split itself apart. A single browser process owns the window, the address bar, and your bookmarks, and it's the most trusted piece of the whole system. Everything riskier gets pushed into separate processes, a renderer process, running Chrome's Blink engine and the V8 JavaScript engine. For each site instance you have open, a dedicated GPU process, a network service process, and a handful of utility processes for one-off jobs like decoding audio. Renderers are deliberately the least trusted part of Chrome, because they're the part directly running someone else's code. Split this way, a page that hangs or crashes takes down exactly one process. You see a single gray tab, not a dead browser. Splitting into processes only helps if a compromised renderer can't reach anything valuable. Two things enforce that. First, the sandbox. A renderer process runs with almost no direct access to your file system, network sockets, or other programs. On its own, it can barely do more than compute. If it needs anything sensitive, it has to ask the far more trusted browser process, and that request travels over Mojo, Chrome's internal message passing system, where every interface spells out exactly what's allowed. Second, site isolation, which Chrome shipped in version 67, mid-2018, weeks after the Spectre vulnerability went public. Spectre showed that code running in a process can sometimes read memory inside that same process it was never supposed to see, which meant a compromised script in, say, an add a frame sharing a process with your banking tab could potentially read that tab's session token straight out of shared memory. Chrome's fix wasn't to patch the leak. It was to remove the shared address space entirely. Every cross-site frame now becomes what Chromium calls an out-of-process frame, running in its own renderer, separate from the page that embeds it. Press enter, and the browser process first checks the URL against a locally cached set of safe browsing hash prefixes, so a no-malicious site can be blocked before Chrome requests a single byte from it. Then comes DNS resolution, a TLS handshake, and increasingly, if the server supports it, QUIC, a transport Chrome helped pioneer that runs over UDP instead of TCP specifically to avoid one slow packet stalling every other request on the connection. None of this actually happens inside the browser process anymore, since Chrome split networking into its own sandbox network service process. That process owns the sockets, negotiates the connection, and streams the response back. Chrome doesn't even wait for a process to become available, it will speculatively launch a fresh renderer process in parallel with the network request, before the response has even arrived, so there's somewhere for the page to go the instant bytes land. And Chrome doesn't wait for the download to finish either. Those bytes are fed into a streaming HTML parser that starts building the page from a response that isn't complete yet. Inside the renderer process, Chrome's Blink engine turns raw bytes into pixels in stages. HTML is parsed into the DOM, a tree of every element on the page. CSS is parsed separately into the CSSOM, a tree of every style rule. From there, Blink's modern pipeline, a project called Rendering NG, runs 5 named stages. Style applies the CSSOM to the DOM, layout sizes and positions every box, producing what the team calls a fragment tree. Pre-paint walks the tree building property trees, and figures out what actually changed since last frame. Paint turns only the changed parts into a display list of drawing instructions. And Composite assembles the final frame. That precision is exactly why some CSS changes are expensive and others are nearly free, change an element's width, and Blink has to redo layout, pre-paint, and paint for everything downstream of it, change only its opacity or transform, and Blink can skip all 3 stages and jump straight to compositing. Once a page is painted, Blink hands the result to the compositor thread, deliberately not the same main thread that's running your JavaScript. That separation is why you can flick scroll a page smoothly even while a script is stuck in a long loop. Scrolling and simple animations are the compositor's job, and it never has to wait its turn behind your code. The compositor splits the page into layers, cuts each layer into tiles, and rasterizes those tiles roughly in order of how soon they'll hit your screen, work that increasingly runs on the GPU through Skia, Chrome's graphics library, with a newer backend called Graphite built to exploit modern GPU APIs directly. A separate, sandboxed GPU process assembles the finished tiles into a frame. When rasterization can't keep up with a fast scroll, you're seeing the compositor's honesty about it, a blank checkerboard pattern where tiles haven't rasterized yet, rather than the wrong content flashing on screen. V8, Chrome's JavaScript engine, never just interprets your code line by line. Source is parsed into a syntax tree and compiled to bytecode by Ignition, V8's interpreter, so the page can start running almost immediately. In the background, V8 profiles which functions actually get called a lot, and hands the hot ones to Turbofan, its optimizing compiler, which turns them into real machine code, specialized around the exact shape of the objects it's seen so far, using inline caches keyed to that shape. See the same shape every time, and V8 calls that call site monomorphic, one check, one direct memory load, as fast as code gets. See more than 4 different shapes, and V8 gives up optimizing that call site entirely. Break an assumption a compiled function relied on, and V8 deoptimizes it, discarding the machine code and falling back to bytecode, a safety net that makes aggressive speculation safe, since a wrong guess only costs speed, never correctness. Underneath all of this, Orinoco, V8's garbage collector, reclaims memory generationally, running old and young generations in parallel on background threads, a change that reportedly cut average compaction pauses from around 7 milliseconds to under 2. Everything you've just heard runs in parallel, across processes and threads, except your actual JavaScript. On any single page, your code executes on one main thread with one call stack. Work gets scheduled in 2 queues, macro tasks, like a timer firing or a click being handled, run one at a time, and after each one, every pending microtask, every queued promise callback, drains completely before the browser is allowed to do anything else. Only once that stack and that queue are both empty does the browser paint the next frame, running any request animation frame callbacks first, all aimed at a roughly 16 millisecond budget per frame to hold 60 of them a second. That ordering is also the sharpest edge of the whole system. If one function runs too long, that single thread simply doesn't get back to anything else. No clicks register, no scroll updates, no frame paints. The tab visibly hangs, not because anything crashed, but because the one thread doing the work is still busy doing it. Every one of those processes still has to manage its own memory carefully. Chrome allocates through partitionalloc, its own memory allocator, built with security as the primary goal. Objects of different types and sizes are sorted into separate typed partitions, with guard pages at the edges of each one, so a linear heap overflow in one partition can't corrupt into another, turning what used to be a working exploit chain into a crash. Inside the renderer, DOM nodes are C++ objects wrapped by JavaScript objects that V8 manages, and Blink needs both halves to be freed together or one leaks the other forever. That's the job of OilPan, a Mark-N sweep collector for Blink's C++ object graph, traced together with V8 as one unified heap. And when your whole system is short on memory, Chrome can quietly discard an inactive background tab, these days picked by a machine learning model estimating how likely you are to revisit it, not just a flat timer, freeing everything it was using while leaving the tab sitting right there in your tab strip, and reloading it from scratch the instant you click back. Increasingly, Chrome tries to do the work before you even ask for it. Back-forward cache takes a full in-memory snapshot of a page when you navigate away, DOM, scroll position, JavaScript paused but not torn down, so hitting the back button can restore it instantly instead of rebuilding it from nothing. It's automatic, but fragile, a single unload event listener left on the page costs roughly an 18 percentage point drop in how often Chrome can use it, which is why modern guidance says never to use one. Speculation rules let Chrome pre-render a page you're likely to click next, fully rendering and running it in a hidden, still fully sandboxed process before you've clicked anything. Service workers sit between a page and the network as a script you control, letting a site respond instantly from cache or keep working offline. For years these were three separately built systems bolted onto Chrome. Today they all run on one shared foundation called MPArch, which is what lets a single tab legitimately hold more than one page's worth of process state alive at once. Put it all together and here's what actually happens between your keystroke and the page in front of you. The browser process checks the URL and hands networking to its own sandboxed process, which resolves, connects, and starts streaming bytes back before the response even finishes. Those bytes flow into a render process, parsed into a DOM and a CSSOM while V8 is already compiling the page's scripts in the background. Style, layout, paint, and compositing hand the result to the GPU process, which assembles the actual frame on your screen, and the entire time, dozens of separate processes did their part without any single one of them being trusted with the whole picture. That last part isn't incidental. Spectre broke a hardware-level assumption that one process can never read another's memory, so Chrome made the process boundary itself the security boundary, the one line strong enough to survive a flaw baked into the chips underneath it. Everything else, the caching and the pre-rendering and the compiler tricks, only gets to be fast because none of it is allowed to weaken that line. Chrome is what systems engineering looks like when 2 billion people use the result every day without ever knowing it's there.